Okay, this lesson is on gas laws and their calculations. The first part of this lesson is just going to be kind of a quick review of what you've learned through the simulations. You can just kind of pause as you need if I go too fast. And then I want to spend more time on kind of going through some calculations. So these definitions are things we've talked about before. We just want to make sure that we understand their definitions because these are the variables that we're going to be talking about. So we're going to be looking at how is changing temperature, how's that going to affect my pressure, how's it going to affect the volume of a gas. So we just want to make sure we know these definitions. So if you need to pause and write these down, go ahead and do so. Here's a review of the different gas laws. So again, these are kind of, we should be getting a good handle on these based on the simulation and the lab. But here's a quick review, right? Or a quick way to kind of summarize what we've learned. So for Boyle's law, we're going to be looking at pressure and volume. And we can tell by the graph that we made. Remember, this is the graph we made in the lab. These are inversely proportional, okay? And then remember, my temperature is not changed. So in the lab, you're at room temperature, you're not changing the temperature of the gas, it's staying constant. For Charles's law, we're looking at temperature and volume, and then I can tell by the graph, right, that it's directly proportional, meaning that as temperature goes up, volume goes up, as temperature goes down, volume goes down. And then my pressure here is not changing. For Gay-Lussac's law, we have temperature and pressure. And again, remember, those are directly proportional. So as my temperature goes up, those particles start increasing in speed. They're going to collide with the outside of the container wall with more force. So that's increasing the pressure. And remember, we're not changing the volume for this. One other thing to note is that there's one other thing that kind of stays constant for all of these. And that's the number of particles or the amount of gas. So we want to make sure we're not changing how much gas we are evaluating or looking at. So I'm not going to pump in more gas as I'm changing the temperature. That's too many variables that are changing at one time, and you're not going to get a good result of what's really causing a change that you see. So just know your number of particles or the amount of gas is also not changing. Here are the equations we're going to use to solve our calculations. So if you need to pause here to write these down, go ahead and do so. And then we'll move on to the calculations. One other note is that you're going to see different units for pressure. Okay, this is kind of letting you know what's equal to what. So 1 atm is going to equal 764, 760 millimeters mercury. These are just kind of used interchangeably depending on where you are, who's using them, what it's for. But just know they're all talking about pressure. Okay, and then for temperature, we always want to use Kelvin. So we're going to convert our degrees Celsius to Kelvin by adding 273. Kelvin is just like an absolute temperature scale, meaning it starts at 0, that's the coldest you can go, and then it can go up to as hot as it's possible. There's no negative numbers, so we want to make sure we convert our temperature Celsius into Kelvin so that it doesn't kind of mess with our calculations. Okay, so let's look at number 1. So the first thing I'm going to do is just kind of read through the problem and look at what my numbers, what am I given? Okay, am I talking about temperature, pressure, or volume? The easiest thing to do is kind of label them as you go. So here I have 22.5 liters of nitrogen, so that's a volume. Is at 748 millimeters mercury, that's a pressure. It's compressed to 725 millimeters mercury. What is the new volume? Okay, so my temperature is remaining constant, and these are the variables I'm given. So my formula is going to be Boyle's law, because my temperature is constant, V1P1 equals V2P2. So now I need to figure out what are my 1s and 2s mean. So the 1 is like your initial. So what am I starting at? Well, it's telling me you're starting with 22.5 liters at 748 millimeters mercury. So that's my V1 and P1. and then it's changed to or compressed to this value over here. So that's my final value of pressure. So that means what I'm looking for is my V2. So I'm just going to start plugging things in. Okay, and then now I can solve for my V2. I'm just going to divide by 725. Okay, and then when you get all of this typed into your calculator, what you should get is 23.2. And then I know my units of volume are liters because that's what I was given in the equation or in the problem. Okay, and then there's an example of how to solve it. So these will be posted, these slides will be posted, so when you get done, if you want to go back and look at some of the problems that we skipped, you can do that. So number 2 is just like the one we just worked out. It's using the same formula, so I'll let you do that one on your own. So let's look at number 3. So we're just going to read through. It says, calculate the decrease in temperature when 6 liters at 20 degrees Celsius. Okay, so this is my initial values, and it's compressed to or changed to 4. So that's my final value of volume. Okay, so I'm looking for my T2. Okay, remember, I have a temperature here that's in Celsius. I have to turn that into Kelvin. So I'm just going to add 273.15. So that equals 293.15 Kelvin. So that's the value I'm going to use for T1. So I'm just going to plug in V1 over T1, V2 over T2. Okay, so that's 6 over my 293.15. Sorry, let me write out my equals 4 over, and then remember that's what I'm looking for. Okay, so we can do a lot of things to try to manipulate this equation, right? The easiest thing to do is just to cross multiply. Okay, so I'm going to multiply these two together. 293.15 times 4 equals, and I'm going to multiply these two together, 6 times T2. Okay, and then now I can just solve it just like I was doing before. So I can divide by 6, divide by 6. So my answer, when I type that in my calculator, should be 195.3, something like that. Okay, and we are not really concerned with sig figs here. We should just, we're not going to worry about that too much for just these practice ones. So just see if you can get close to the answer that I got. Okay, number 4 is just like that. So again, don't forget though, when you do this, you have temperature in Celsius, you have to convert that into Kelvin. Okay. All right, let's look at number 5. So it says Mary's backup oxygen tank reads at 900 millimeters mercury. So that's going to be my first pressure while on her boat. The temperature is 27. So here's my T1. When she dives down to the bottom of an unexplored methane lake on a recently discovered moon of Neptune, the temperature will drop down to minus 183 degrees Celsius. So there's my T2. Okay, and so now what I'm looking for is the final pressure, P1. Okay, remember I have some temperatures in here that are Celsius. I have to convert that into Kelvin. So let's do that first. So T1 was 27, but I have to convert that into Kelvin by adding 273. And T2 was minus 183. And again, I'm going to convert that by adding those two together. So when you add those in your calculator, you should get this is 300.15 and let me double check that last one. I think I tried to do that in my head and I may have. messed my decimal place. Yeah, that's right. Okay, 90.15. So there's my temperatures in Kelvin. Okay, so now I'm just going to plug it into my Gay-Lussac formula, which is P1 over T1 equals P2 over T2. Okay, so I'm just going to go through and plug it in. So P1 is, let's do 900 over T1, right, is 300.15. P2 is what I'm looking for, right? That's what I don't know. And then my T2 is 90.15. Okay, so again, I'm just going to cross multiply. So we'll do right here, 300.15 times P2 is equal to these two multiplied together, 900, 90.15. And when I divide, we should get something around 270. Let me just double check since I was unsure about my place value. Yeah, 270.3. And then my units of pressure, since I'm using millimeters mercury here, I'm going to use millimeters mercury. Okay. Number 6 is the same type of problem. Okay. Don't forget to convert to Kelvin. All right, let's look at number 7. Yes, okay. So on your notes, on the chart, on the top where it talks about the different laws, there's something called the combined gas law. So what they've done is just combined all the formulas together into one formula. Because it turns out that if all of them are changing, they all still have the similar relationship. So we can actually calculate one when two things are changing, as long as our amount of gas stays the same. So again, our number of particles, our amount of gas is staying the same, but now we can alter multiple variables of pressure, volume, and temperature and kind of see how that affects the others. Okay, so we have this, so make sure you write this formula down in your notes. So let's go through and see if we can plug this one in. It's the same thing, it's just more numbers. So a volume, 106 liters. So there's my V1. Okay, when the temperature is 45, here's my T1, and the pressure is 740, P1. What is the volume? So I'm looking for V2. Here's my T2 and my P2. Okay. So I'm just going to plug in my numbers, okay? And then don't forget, I have to convert this into Kelvin by adding 273. Okay? So P1, 106. V1 is, that is V1. P1 is 740 over T1 is I think it's 318.15. Okay, and that's going to equal, what is the volume? So I'm looking for that. So 780, there's my P2, V2, and then my temperature to 293.15. Okay, so remember I've changed those to Kelvin. Same thing, I'm just going to cross multiply. So I'm going to do these. So I get 106 times 740, I have to write smaller, times 293.15, okay, equals these 318.15 times 780.0, and then V2. Okay, and then again, it's probably easiest to go ahead and multiply these together. So when I do that, let me just change the color. 318 times 780, you get 248,157. Okay, so Then I can divide by 2, 4, 8, 1, 5, 7, and then those will cancel. Divide this side by 2, 4, 8, 1, 5, 7. And then at the end, you should get something along the lines of 93.5 liters. Okay, as long as you get something close, the way that people round is a little, so as long as you're between, 93 and 94, okay, that should be fine. So same thing, you're just plugging in more numbers, okay? It's just a little bit more calculation, a little bit bigger numbers. As you can see, 248,000 is a pretty big number, okay? And then here's number 8. It's another combined gas law, so it's very similar to number 7, okay? And then you have a homework module to do after this, where you're going to get some more practice doing a couple of gas laws and just some general questions about gas laws. There's a bunch of extra practice problems on the notes page. Those are not required. Those are optional. I will upload a key to those hopefully sometime this in the afternoon. So just keep a lookout for the key if you choose to do those to get extra practice. Reach out if you have any questions.